by Abel Chen on outer Plasmasphere Irregularities and Plasmatails.
There have been many observations of irregular structure of light ion measurements on polar orbiting satellites as well as near equatorial satellites. The most prominent of the irregularities observed in the equatorial plane appear to separate from the inner plasmasphere has been called detached plasma region by Chappell et al. This paper will explore through a model the hypothesis that on a global scale, this detached region detected by OGO3 and OGO5 are filamentary extensions of the plasmasphere called plasmatails. The first slide illustrates roughly how the plasmatail can be produced by temporal variations in a continuous magnetospheric convection field. The top panel shows steady-state convection flow pattern with a shady region representing high-density plasmasphere. With the enhancement of convection field, the outermost closed flux tubes will become open, resulting in a transport of dense plasma towards the magnetopoles, thus producing a broad extension of the plasmasphere in the afternoon sector. If the electric field maintained higher, the broad plasmatail will gradually thinning out while the base of the plasmatail remains unchanged near dusk. However, if the enhancement subsides, the co-rotation electric field will dominate to greater radial distance. This will cause the base of the plasmasphere extension to co-rotate with the Earth, while the end of it remains attached to the magnetopoles. The result is a formation of a thinning plasma tail, which will wrap around the inner plasmasphere. The equatorial convection model used here was originally set up by Stern on the basis of OGO6 electric field measurements. The top panel illustrates the thermoplasma flow pattern due to this model. Generally speaking, the flow direction is sunward. Unlike the teardrop model Dr. Chappell discussed this morning, in which the field strength is spatially uniform, the field strength tends to increase with respect to increasing L coordinate. It implies a partial sealing in the inner magnetosphere. The resultant flow pattern, including the Earth's co-rotation, is shown at the bottom panel. The shady region represents steady-state plasmasphere. Of course, the steady-state configuration cannot explain the observed irregularities. Thus, we assume that the amplitude of the convection field is proportional to 1 plus 2/3 times Kp, as suggested by Dr. Heppner from his OGO6 electric field measurements. Assuming a dipole field and that field lines with L coordinate greater than 10 effectively open and depleted of plasma, the flux tubes are traced backwards in time along their drift paths to determine how long they have been closed and on the day side. As a primary source of ionization comes from dayside ionosphere, presumably the longer the dayside closure time is, the higher the density would be. This slide shows the H plus density detected on OGO3 for pass in July 1966 after a magnetic storm. Light ion density is plotted as a function of L for the inbound and outbound portions of this pass. The theta trajectory is superimposed in the lower part of the slide on the computed closure times at a universal time characterizing the pass. Shadings in this and subsequent slides are used to depict ranges of closure times. The darkest shadings correspond to longest closure times and hence the highest density, whereas white correspond to depleted flux tubes. On the inbound path, a single plasma pulse transition is detected near L equal to 3 at night in agreement with the model. On the outbound path, the isolated patch of enhanced plasma density observed is interpreted by the model to be a transversal of a thick extension of the plasmasphere. The satellite emerged from the main plasmasphere into a trough and then through the enhanced density of the plasmatail. Another observation of a thick detached plasma region near dusk is shown in the next slide. This time, the measurements were made on the outbound path of OGO 5 in September 1968, again near a magnetic storm. An enhancement of the line ion density is seen near L to 8, far from the inner plasma pulse along the satellite trajectory. Again, the model computation produced a broad extension in the noon-dusk quadrant, which cuts through the satellite trajectory in agreement with the observations. The occurrence of multiple levels of closure times in the model indicates the importance of previous storms on the density distribution. The solid lines separating regions with distinctly different closure times and hence densities are not just boundary markings. They correspond to regions with 6-day closure time, that is, they are thin plasma tail region, which in part could qualitatively account for some of the observed fine-scale density fluctuations. These examples show a plasma tail interpretation of observed pronounced detached regions in the afternoon is plausible, but what about irregularities observed at other local times? The next slide shows an OGO 5 path on which a large density enhancement is detected before noon near L equal to 4. Such a feature may also be a plasma tail, as the model produced a tail-like enhancement of line ion density in approximately the same location. This tail is the result of a previous storm. We didn't have time to include the outbound path in this slide. However, the plotted profile generated does show little irregularity as the model predicts. Irregular structures has also been detected in the density profiles near dawn. The next slide shows an example of such structure as observed on OGO 5. These paths occur during a period of relative magnetic quieting. Note the structure near L equal to 4 on the outbound path at dawn. The model shows how such complex structures may reflect multiple tail traversals. The inbound path also seems to indicate a detached plasma region with small-scale density fluctuations. It is tempting for us to explain this in terms of the satellite skirting along the thin plasma tail predicted by the model. But considering many simplifying assumptions used in this model, it is just as tempting to use this example as a failure on the part of the model to explain all the observed features. Although the model employed produces structures in general agreement with many of OGO 3 and OGO 5 density profile, which were studied at diverse local times and storm conditions, we do not want to imply that all of the irregularity observations can be accounted for by this model. Temporal variation in the convection on a period shorter than 3 hours and or localized perturbations in the magnetospheric electric field resulting in ripples in the plasma pulse, as suggested by Park and Carpenter, could produce similar features. However, unless the assumptions used in the model are grossly out of step with reality at all times, the plasma tail hypothesis appear to offer a reasonable interpretation for many of the observed irregularities. I don't have time to show a slide which the model didn't reproduce, so I'll close my talk here.
Other comments or discussion?
I think it's important to, in a model of this sort, to worry about some of the effects that I mentioned this morning, at least in terms of the effects of the energetic particles in causing potential spatial gradients in the electric field, which the smooth time-varying model does not have. And I think in future models it might be worthwhile to try to model some of the spatial gradients, if possible, both at the inner edge of the plasma sheet and potentially in auroral arcs where the electric field is observed to change quite rapidly and over small spatial values, which might change very drastically the origin of a tail as opposed to very choppy tearing away type motion of the cold plasma.
Yeah, we very much agree with what you say, and we plan to do that.
I'd like to say, perhaps in support of this paper, that in the studies we've made with VLF techniques, looking at the equatorial plane and plasma structure, we often observe a kind of trough in that one sees an outlying, one looks in a radial direction and observes a trough-like region followed by an increase in density, and typically in time, as the ground station rotates, one tends to see this disappear, often in the afternoon sector. And so I would say that just looking at the totality of observations so far, that the trend that one very often sees is a structure which exhibits a rather large, either temporal or spatial distribution, and that which eventually disappears, often in the dusk sector. So that I would say that there is at least a good deal of evidence to suggest that this mechanism is operative. We also see recently one of our people has been investigating an equatorial profile that looks something like this, a very deep notch or depletion that might be the inner edge of, that might represent a one of these effects that you drew of a tail which then wraps around the night side of the Earth. Observations were made for about 14 hours across the night side, and this deep notch or hole in the profile was observed throughout this period, suggesting that indeed such nearby dense regions can persist for long times. In this case, we couldn't determine that it exhibited a termination at this point, but so I'd say we are seeing something supporting this indeed.
Don, could I ask you a question? At what L shells do you see this tail effect?
Well, these range from 3 to 5, and so they're typically mid magnetosphere, inner magnetospheric effects. This was seen at about L of 5.3, I believe, during quieting, when indeed one might expect such a feature to form. One also sees what appears to be very irregular structure, again possibly due to the substorm modulation of the system, which might well be greatly amplified by the irregular convection. And one also sees a larger electric field, as you were saying this morning, perhaps in the dusk sector. If you look at, again, the bulk of the data, the